traffic become very congested, then everything is unpredictable. Okay, maybe it will take you 10 minutes, or sometimes it will take you half an hour. So this gray point is the actual data. So this both part that what I mean as a demand uncertainty and the supply uncertainty here. So the key contribution of this work is that we add this component into the original framework of cell transmission model, making it to stochastic cell transmission model. And there's some, very detailed mathematical formulation that we use some bilinear system, okay, so that we can separate out what is the likely scenario of the next step of the time model. And we combine them together, calculating the probability of each possibility that we actually can have in the next time step. And we combine them to reduce the dimension of the data using finite mixer distribution here. And the output that we can get is some kind of estimation or prediction of the cell density. Cell density means, okay, at the first kilometer of expressway to say 500 meters apart, how many vehicles should be in that location 5 minutes later, something like that, okay? So this is example of the implementation here. So along this expressway, we will have the location that we have the sensor, upstream and downstream. What we don't know is what's happening in between. Apart from the location problem, we also have the problem with the data across the time, okay? Because the actual implementation is, for example, I need to send the data real time from the expressway in Bang Pi Suk Sawat, okay? Real time back to the major ITS center in Bang Khen, okay? That's the key center of XZ. And the problem is we can't send the data every minute, every second. The actual sensor sends the data every second. But if I send the data back every second, there will be a bottleneck of the internet network around the Bang Khen center. So what we can do is we only can send the data every 5 minutes. Okay? So at 8 o'clock, I will have some data of the upstream sensor as well as the downstream sensor. I don't know what's happening now here. Later on, 5 minutes later, maybe I have some data, okay, here at 5 past 8, okay, upstream, downstream. I also don't know what's happening between 8 o'clock in the morning up to 5 past 8, okay. So that's also the data missing that we have here. So traffic state estimation answers this question that we try to estimate both the traffic condition along the segment of this highway without a sensor, as well as between the time period that we don't have the data here. So the way we did it is we basically use this stochastic cell transmission model here, and we put the traffic sensor data as a kind of constraint of the upstream and downstream, and try to sort of adjust the flow model, okay, so that the actual output of the flow moving along this segment and at the downstream and upstream model actually fit with the real-time data. So that's a sort of traffic state estimation that I mentioned about here. The other related problem is traffic state prediction. Okay, prediction is actually easier because we don't have the downstream constraint. We only have upstream. I just need to know what is the upstream flow, and then I just propagate the flow. I just have a model, right? I can put that there will be 2,000 vehicles arriving at this point. I want to know how they actually move from upstream here to the downstream, okay? So I just implement this. The problem with the prediction is that we need to predict the demand in the future. For state estimation, we have exactly the data, what happened in the past. In the past half an hour, we know exactly what happened around the sensor area. But for the upstream, we don't know any, for the prediction, we do nothing in the next half an hour. So what we do is that we build some kind of spatial temporal correlations of the demand and supply relationship, and we use the most up-to-date data, let's say at 8 o'clock in the morning, and look at the database. It's like the expert system. Look at the pattern that actually can give us the best prediction for the next half an hour. Okay, then we use that as an input to this stochastic cell transmission model here. And then we use exactly the same model with the predictor here, and we got the output in terms of traffic density and travel time. Okay. So I think that's the only equation I have on my slide. So what we have here is that, let's say we're thinking about the traffic prediction. We know the traffic state up to this point here, 7:30 in the morning, okay? And we also know the historical data in the past 1 year or past 6 months of the traffic situation along this highway. So I can actually use, okay, this covariant matrix here between the historical data across the time, compare with the error that we actually make from the prediction in the previous time step that we already have the data, okay? And then we can make a prediction for the next time horizon here. So it's pretty straightforward concept here. So this concept called rolling horizon. So I know the data up to a certain time. Then I use this data with the statistical knowledge of what's happening in the past with a similar situation. Then I make a future forecast for the next half an hour or an hour. Okay. So this is an example of the implementation of this. So this is an expressway sensor data. So this is a center that we have here in behind Kasetsart University, okay, so Bang Khen Center. And actually each of the expressway, they have their own toll plaza, okay, and they have their own center here, and they will send the sensor data collected at the toll plaza, okay. But we can only pull the data to this main server here every 5 minutes. So that's why we have to come up with this kind of structure here. So this is the kind of data we will have that, okay, we have the ID here at this date, at this time. The interval can be every 1 minute or every 5 minutes. We will have the flow, speed, the density, level of service, okay. Then our role is to basically predict the state that we actually have along the highway without the data. So let me just show you some example. This is the project in Thailand. We just started actually this morning. We just peacefully passed the first meeting. Okay, so hopefully we will have this system ready for Bangkok soon. But what we did already is we actually carry out this test for the expressway system in Japan. So this is example between I think Toyonaka City to somewhere in Osaka. Okay, so this is some expressway segment in Osaka. So the way we did is that we need to build a model along this expressway. Okay, so this is the starting point of the expressway here, kilometer 0. Downstream to, I think the whole segment is about 12 kilometers here. The dot here is the location of the sensor. So that's where we actually have the data. And we divide the highway into different segments. Okay, so this different color means it's different block, it's different cell. Okay, so we have this online model that will predict or will estimate how the traffic move from upstream to downstream here. So example is that, oh sorry, the actually traffic move from here from right to left direction. Okay, so we test with the actual data on a certain day that we actually have the incident here. So there will be some different record of the traffic incident, traffic accident at 8:30 in the morning, and location of this is between this cell here, okay, that we detect here. So we want to test whether the model can pick up, okay, this kind of effect that there is an incident, okay, how long will the queue be? Where will be the bottleneck, okay, how we actually resolve this queue? How long the queue will last, okay, this kind of question that we have. So this is the first location of the incident, okay, that we test, 1599, okay, and create this traffic jam backward here because the traffic direction is from right to left, okay. So the queue, of course, move from left to right here. And this is another incident that we have the data here, okay, and the jam actually moved back upward quite far away, and several incident locations that we show over here, okay. So the type of output we got from this kind of system is that, for example, here we can have the time clock, okay. So each of these graphs is the density of each of the segment of the cell along the expressway. The actual black dot here, okay, if I can point it out here, is the actual data. Okay, so the purpose of testing the model is we want to know how close our model to the actual observation in the real world. So you can see is that if there is no problem at all, then the traffic prediction, okay, which is our red line here, is more or less the same with the actual data. Okay, so state estimation is perfect. Even we actually have the data not exactly every second or every minute. On the other hand, on the location that we start to have the accident, okay, the simulation model, which is this red line here, can also pick up, okay, the density. So it means that there is an accident. So the traffic actually start to build up. The queue start to build up, okay, upstream. So we actually can also pick up that quite easily here. Some good example here is how big the queue can actually jump up on certain location here. Okay, I don't have time to just jump into the detail of what exactly this location on the expressway, but it's just to show that actually we have ability to replicate the actual data by this kind of simulation model here. Okay. So this is just a spillback and spillback of the jam in different locations that we actually test here. So I think that just give all of us a kind of So just a brief concept of when we actually move from the actual research to the actual application, it's actually possible, but you also need to do a lot of work, okay, to please the user. And I hope that I can give you a lot more detail, but it will involve something like 200 equations, and I hope at least this gives you some, some case and some motivation to actually move your research to the actual practice here. Okay, thank you very much.
I have a question on the sensor location. Right.
Okay.
Is there any research to support how to pick the locations and the number of sensors to stay on the freeway? For example, from this slide, you pick the location when there's network change, like from on-ramp and off-ramp, but shall you put near the ramp or in the middle, or how many? If it's 5 kilometers, should be 2 or 3 sensors. Is there any research and then test with the data to determine the number and locations?
Yeah, that's a good question. So it depends on the applications. Okay, so if your main application is to do the performance measurement, okay, it means that you don't want to detect any accident or any abnormal queue, then I think the location around the on-ramp, off-ramp should be quite sufficient. Okay, given that we have a good data of how the flow density characteristic of the highway can actually we have. But the problem is that if you want to apply this system to, say, incident detection means that if there is any some accident happen on the expressway in Bangkok, I want the system to pick up that incident within 1 minute, right? Within 1 minute. And the accuracy is, say, 95% accurate. Then we need a sensor that the detail and the interval of sensor reduce, okay? We actually have a research on the actual effect of the sensor location and how quick you can actually detect the incident. But the detail, and I mean, there is no like off-shelf solution. So everything is like case by case, but there are some research that you can apply to design your location of the sensor. The other thing is that apart from the on-ramp and off-ramp location, we should look at the traffic condition that you have, okay, in your system. For example, where is the normal bottleneck? Okay, where's your normal bottleneck? Where's your normal queue spillback location? And that kind of thing can also help you to locate the sensor, because the sensor data will be useful if we actually detect some congestion pattern. If you locate somewhere that there is no queue, you just get the free flow data. I mean, there's nothing. But if you locate somewhere that there is some transition chain between the free flow segment to the congested segment, then you actually can use the sensor data quite a lot, okay?
Okay, just to follow up the questions, in your expressway, you have 30 kilometers, but you only have 6 sensors.
Yes.
And you show that the results are pretty good.
No, that's a different case. Sorry. This is for the Bangkok expressway.
Right.
We only have 6 sensors.
So is that sufficient?
We will see.
We haven't done that yet. Okay.
So we just started the project now. But this one, I'll show you here. This one, they have a lot more sensors. It's only about 12 kilometers, but they have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's almost every kilometer. And I think that's more or less a standard in California as well. But in Bangkok, I think the segment that we chose, already they have the highest number of sensors. The other segment, they don't have any sensor at all.
So I just wonder, for Thailand's case, because there's a limitation in terms of the budget. So how many sensors is sufficient for this particular application?
SCTM, yeah. I think what we test is that, for example, in this case here, we also carry out the test that we do not feed the model some of the sensor data. And it came out that I think if we have the segment of something like within 2 or 3 kilometers, it's still okay. Because normally it depends on the queue length and it's, the backward wave, something like that. But once we take out, let's say that what we did is we take out these 3 sensors here. So that means it's covered like about 4 kilometers apart. then so many things can happen within this 4 kilometers. So for the case of Bangkok, I'm not saying that we can actually get very good estimation. The problem is that we cannot talk only about sensor without explaining them what are the main use of all this data. That's why this kind of thing is a minimum budget requirement. And the reason they have the sensor on that expressway segment is because it's built in within the BOT contract. Okay, so it's actually installed during the construction process.
Okay, just a comment. You mentioned about where to place the sensor at the active bottleneck. In fact, there's many cases that you want to place the sensor at the hidden bottleneck, which is not discovered until something happened.
Yep, sure, exactly. Yep. So this kind of thing is, first of all, I think it's kind of evolution process. So like for example, from this 6 sensor, at least I saw some pattern of traffic now. Okay, even with 6 sensor. The pattern of traffic is that there is no congestion on that expressway, so maybe we can get a good prediction. Okay, so thank you.
So thank you, So I'm not quite sure about whether I have understood perfectly about your presentation, but my question is, haven't you validated your model in terms of the accuracy of travel time forecasting along the expressway corridor, like for next 30 minutes, or has forecasting something like that? And actually, because we are doing kind of the stochastic modeling, the predicted travel time along the expressway corridor should be London variable. So have you validated the result in terms of not only the mean, but also in terms of the variance or the PDF, something like that?
Yep. Yeah, we did, because one of the key output from this system, first of all, we know the density. We know the flow propagation. What we did is that this is for the work with the other lady student. She's completing now, Lucia. What Lucia did is that she developed an algorithm, okay, to estimate the distribution of travel time. It's based on this stochastic flow, and then we validate with this case as well as there's some segment of the California freeway. The data is okay, the accuracy, but we will have some slight problem about the actual distribution shape. Okay, right. we got a very strange distribution. For example, people think that it should skew left, okay, but somehow our estimation show that the distribution skew right, okay, and I think that's mainly because the way we simplify the mixture distribution in the model. So that's something that we're trying to do, because one of the key output that we aim to have for this system as well is for the travel time estimation and the travel time prediction. Yes.
Yeah. Thank you.
Thank you for the presentation. I think it's a great model. And I like to see what's going on with Thailand also. But the question I have is that, yeah, in normal circumstances, you can actually predict what's going on.
Yep.
But in Thailand, I feel like there are something that is uncommon elsewhere. For example, those law-abiding drivers, they just want to stop anywhere. They create their own lane sometimes.
Yes.
The thing is, behavior that you can predict would be, okay, I don't know what's going on with that, okay? And sometimes there's no traffic at all because the police stop every vehicles going to expressway.
Yeah.
And with the sensor say, hey, no cars, there should be no traffic jam. But the thing is, it's a big traffic jam, could be kilometers from that.
Yeah.
How would you expect the idea to actually solve that for your prediction models here?
Right. Okay, so that's a kind of what we call non-recurrent, right? So I think there are 2 components here. The first is the what we call the stochastic part of the behavior, right? So I also experienced this myself. So some truck just decide I'm just going to stop somewhere, right? So that part should be. I need to explain that this model is not like an off-shelf model. So when we apply the model, we need to calibrate the model to the actual situation. So for example, the diagram down here, okay, this one is from California. But I expect that if we plot this diagram for Bangkok, it will look also different. And maybe a very high degree of uncertainty. Because the more thing we can have to go wrong, the higher uncertainty we have. So that probably can be accommodated to some extent. Okay, I'm not saying that this